Hello everybody, welcome to Catalysis, Discovery and Technology Tool, where we discuss and explore catalysis and its future in science and medicine. In this first lesson, we will be introducing catalysis. So, let's get right into it. This lesson will answer the questions: what is a chemical reaction? What is a catalyst? What does a catalyst do? And what are types of catalysts? What is a chemical reaction? In the broadest term, a chemical reaction is the rearrangement of chemical bonds. Here, two carbon monoxide molecules will react with one oxygen molecule to produce two carbon dioxide molecules. This is also represented in an equation that you can see above. Carbon monoxide is a byproduct of combustion. It is commonly produced as exhaust in gasoline and diesel engines. Carbon monoxide is acutely toxic, so it is necessary to convert it to carbon dioxide, which is significantly less dangerous. Carbon monoxide replaces oxygen in the bloodstream. This causes serious damage to tissues, as they are starved of oxygen. We need to get rid of carbon monoxide before it can poison anyone. This means this reaction needs to happen quickly. So how do we make reactions happen quickly? To understand this, we need to look in detail at what happens when molecules react. For molecules to react, they need to bump into each other with enough energy. Not all collisions have enough energy to react. Sometimes the molecules will just bounce off of each other without reacting. So what are the measurable properties we can adjust to increase reaction rates? These molecules are all gases and will be bouncing around randomly. We measure the average speed of the molecules as temperature. At low temperatures, these molecules will be moving slowly. Increasing the temperature not only increases how frequently they collide, but also increases how hard they collide. Increasing temperature will increase reaction rates. If there are more molecules in a given volume, they will be more likely to hit. For gases, adding more molecules increases the pressure, and for liquids, adding more molecules increases the concentration. Increasing concentration of reactants will increase the reaction rates. Thinking about this in another way, there are two possibilities when molecules collide. Either they have enough energy and react, or they do not have enough energy and will bounce off. This is commonly shown in a graph. The reaction coordinate is how far through the reaction we are. Reactants are on the left, and products are on the right. The height of the hump is the activation energy. If the reactants meet without enough energy to get over the hump, they will not react. The height of the hump is the activation energy. If reactants meet with enough energy to make it over, they'll react and get extra energy on the way down. This extra energy is the heat of reaction. Sometimes you must put in the heat of reaction, but that's not important now. Increasing the temperature increases the average energy of the molecules. Even at low temperatures, some molecules will have enough energy to react. For example, assume there are 100 collisions every minute. At 25 degrees Celsius, it may be that only 1% of molecules have enough energy to react. The reaction rate will be 1 molecule per minute. If we increase the temperature to 100 degrees Celsius, it may be that 25% of the molecules have enough energy to react. The rate has increased to 25 molecules per minute. The study of reaction rates is a large portion of chemical engineering, which is called reaction kinetics. Let's reconsider our example of car exhaust. We need high temperatures and pressure. Is it reasonable to increase the temperature of car exhaust to react away the carbon monoxide? Probably not. The gas was already exposed to very high temperatures in the engine, and these were not enough to get rid of the carbon monoxide. So what can we do? Catalysts are broadly defined as anything that changes a reaction rate but does not participate in the reaction. Catalysts can be anything from metals to acids and bases to proteins. Catalysts typically work by rearranging one or more of the reactants to make it active. Once activated, the energy needed to react is reduced. Thus, a higher portion of molecules will have enough energy to react. Put another way, and the activation energy is also reduced. Catalysts make it easier to get to products, but catalysts will not change the overall energy balance or change the equilibrium position of a reaction. So what does a catalyst do? Typical catalysts used for the reaction we are considering are metals like platinum. Platinum holds onto oxygen molecules and activates them by weakening the bonds between the two atoms. When a molecule gets close, it weakly binds to the platinum surface. When two carbon monoxide molecules approach the activated oxygen molecule, it is now much easier to react. The bonds form between carbon and the activated oxygen. The bonds between the oxygen atoms and the oxygen molecule is broken. The weak bonds between oxygen and platinum is also broken. Note that while platinum was involved in activating the oxygen, it was not consumed in the overall reaction. The mathematical effect is that the activation energy is reduced. This means that at the same temperature, a higher percentage of molecules will have enough energy to react, and that means that the reaction rate has increased. These types of platinum catalysts can be found in every internal combustion powered vehicle today. While it may seem like it would be expensive to have platinum in every car, the mass of platinum is not important. It is important to have a high surface area of platinum, represented by the grid below. This is accomplished by putting extremely thin coatings on high surface area supports. Another side note, if the catalyst binds too strongly to a reactant, this will slow the reaction down. If it binds too weakly, it does not activate the reactant and again does not help. A moderate binding is needed. This is known as the Sabatier principle. So what are the types of catalysts? Since catalysts are broadly defined as anything that reduces activation energy while not being consumed, there are many types of catalysts. These include some inorganic ones, like metals, metal oxides, and acids and bases. We also have biological catalysts, which include enzymes. We've already seen an example of a metallic catalyst, platinum. Platinum is a heterogeneous catalyst because it is a different phase than the other reactants and products. Acid-bases catalysts and enzymes are typically the same phase as their reactants, usually liquid. So what are enzymes? An enzyme is a biologically derived catalyst. They are almost always proteins, and they are typically very specialized. They may catalyze only one reaction. Enzymes can dramatically increase reaction rates, sometimes by as much as 10 million times. So what are the advantages to the different types of catalysts? In a heterogeneous catalyst, only the surface is utilized. The reactions have to diffuse to the catalyst. The products have to diffuse from the catalyst. And separating the products from the catalyst is very easy, since they are separate phases. In a homogeneous catalyst, all of the catalyst is utilized simultaneously. There is no diffusion needed, and separating the products from the catalyst can be very difficult. So what did we learn today? Catalysts increase reaction rates by decreasing activation energy. Frequently, this is the only viable way to increase a reaction rate. Catalysts come in many varieties: biological, enzymes, inorganic, heterogeneous, metals, metal oxides, etc., and inorganic, homogeneous, acids, bases, etc. Heterogeneous catalysts require more catalysts since only the surface is used, but the products are easy to separate from the catalyst. Homogeneous catalysts require catalysts, but are very difficult to separate from the products since they are the same phase. And that is all that we have for you today. Thank you so much, guys, for watching, and have a good one.